Alright, so the species that was given today, or the coordination compound, was MnNO2 NH3 3-. And so let's get some things off right off the bat. We can determine what the shape is, what kind of coordination compound, and what type of ligand we have. So let's start off with the shape. In most cases, it would be smart to draw out the valence bond theory and then determine the shape. It's just easier for me to do that, but luckily in our case, we can tell that this is going to be octahedral. This is going to have a coordination number of equal to 6 because the central atom is going to have 6 electron groupings. And then lastly, we can determine that the NH3 is going to be a strong field ligand. And we can discuss more about that later, but let's just get straight into this. So the oxidation state for Mn is 2+, and that's because we have a minus on our compound, and NO2 3 is a negative charge. So Mn is going to have 5 electrons in the d orbital. The reason why it's 2+ is because usually we would have 2 electrons in the 4s, but those electrons are taken away, and so that makes it more positive. Now we need since we determined that our ligand is strong, we need to pair up these electrons. So we're going to then add pairing energy. And this is going to make the electrons now pair up. So let's come down here. Let's pair up the electrons. So we're going to have 1, 2, 3, 4, 5. Okay? And now, since we have these electrons paired up, now let's just group the orbitals that we're going to hybridize. In this case, it's going to be 2 of the 3 d orbitals and then all the 4s and 4p. Okay? We're going to add another arrow. And this is going to say hybridize. Okay, and let's come down here. Let's draw our electrons again for the 3D for Mn 2+. Okay, and now we need to name this these hybridized orbitals, and this is going to be D2sp3, and this is a inner d orbital complex. Awesome. Now we have 3 NO2s and 3 NH3s bonding. So this is where these bonds are going to occur in the hybridization state. Okay, and so we just need to write that these electrons, we're going to have 3 NO2 sigma bonds, just add the charge, and 3 NH3 sigma bonds. Okay, and last thing, we need to label each of these 3, I guess, different diagrams. So this is going to be the ground state. Okay, and then we're going to come down here. This is going to be the excited state. And then last, we're going to have our bonded state. Okay. Now let's move to the crystal field theory, or CFT for short. So same as before, let's put in these electrons. So we're gonna have 1, 2, 3, 4, 5. And now the difference between the crystal field and the valence bond is we're gonna split our orbital into 2 different sections. We're gonna have the T2G and the EG. And I'll explain the importance of these 2, but we need to name these. So this is going to be dxy, dxz, and dyz. Up here, dz squared, and then dx squared minus y squared. Okay, now the importance about these is these orbitals down here never intersect with the central Mn2+ compound. And then these ones are in direct I guess contact with the Mn2+, okay? Let's fill out this. So let's first just ask ourselves, is this a high spin or low spin? And the only way we can determine this is, 1, through our strong field ligand. It's going to make it a large splitting energy. Okay, so that's going to help us. But we can also have no spin. But in this case, we have a difference. So if we said we had a weak field ligand, and that would be high spin, you can see that we filled this the orbitals differently. These electrons can come up, there's not as much energy required to jump up onto this upper D deck, I guess. But when we fill this here, these electrons have a lot of space and energy that they need to get through in order to get up here. So let's fill it out. We're going to have 1, 2, 3, 4, 5. And this is different from the weak field ligand. So we're going to come down here and we're going to say that this is a low spin. Okay? Now we can also see that this and this is exactly the same as we drew in our valence bond right here. And if we come all the way to our excited and bonded state, you can see that these are the same and they have to be the same. We know that this is going to be paramagnetic. Reason being is when there's still that lone pair right there. If there's another electron right here, then it'd be diamagnetic. But in this case, it's going to be paramagnetic. Okay? Now, let's determine the pairing energy and which one's stronger. In this case, the splitting energy, since we have a strong field ligand, is going to be larger than the pairing energy. Well, hopefully you found this informative, and let's get an A on this exam.